Good morning, children. Today we will discuss about semiconductor lasers. Let us go to the presentation. Semiconductor laser. In the name itself, we have conductivity. Semiconductivity. Semi means half, conductor, conductivity. So here, what is a conductor? Which allows the flow of charge in one or more directions is nothing but conductor. Conductor means which allows the flow of charge in one or more directions. And what are the insulators? Electrons does not flow freely. Okay, in which the electrons does not flow freely are nothing but here the insulators. So semiconductor laser. Now let us see the construction and introduction part. A semiconductor, it is a material which conductivity lies between those of conductor and insulator. Semiconductor it is a material whose conductivity lies between those of conductors and insulators. So we have two types of semiconductors: intrinsic semiconductor, extrinsic semiconductor. What are intrinsic semiconductors? Nothing but pure semiconductors. That means which a pure material, the host material we can say, intrinsic semiconductor. Extrinsic semiconductor is nothing but doped semiconductors. That means which we are use some quantity of the another material in the host material. That is nothing by adding a dopant or by adding impurity. The materials are nothing but extrinsic semiconductors. Extrinsic semiconductors, again, they are divided into two types based on the majority of charge carriers. Based on majority of charge carriers, these extrinsic semiconductors divided into two types: N-type, P-type semiconductors. In the case of N-type semiconductors, electrons are the majority charge carriers, and in the case of P-type semiconductors, holes are the majority charge carriers here. Now let us see the pictorial representation, and here we are seeing here the p-type and n-type semiconductors. This is a laser diode. This is a laser diode. Here by taking the p-type and n-type semiconductors, and this is the metal contact. Metal contact. Here we have one more metal. The opposite faces here metal contact. Here this is metal contact, this phase, and this phase down phase metal contact, and polished phase. Here this is the polished phase. That means the n-type semiconductor upper surface and p-type semiconductor lower surface partially polished. That means these two phases, they act as the resonant cavity. Upper surface of n-type n-type and lower surface of the P-type semiconductors, one is polished phase, another one is partially polished. This acts as the resonant cavity here. And here we will obtain here laser output can be obtained from the depletion region between the PN junction diode. And this is a very thin layer which is about 0.1 micrometers here. And here we are giving power supply to the metal contacts. This is a positive and this is the negative terminal of the battery. And here we have the reference surface, and here what is the depletion region? So whenever the holes which are present in the p-type semiconductors are joined with the electrons with the n-type semiconductors, what will happen when these two joined? Here we can obtain an electric field. So because of this electric field, the holes and electrons, they may not flow. So what will happen here? We can obtain a depletion region or depletion layer, depletion region. So here this is the PN junction region, PN junction. And here this is the depletion region between PN junction, which we can obtain here from the laser output here. And let us see the construction of semiconductors. Active medium. Here, commonly depletion region acts as the active medium. Commonly depletion region acts as the common active medium. And if we consider gallium arsenide, this is also the active medium which we are using for the p-type and n-type semiconductors here. And pumping source, forward bias. What is forward bias here? P-type semiconductor is connected to the positive terminal of the battery. Here, forward bias. P-type semiconductor is this one, P-type. It is connected to the positive terminal of the battery, and N type which is connected to the negative terminal of the battery. This is the positive and this is the forward bias. So under the influence of forward bias, electric field conduction electrons will be injected from N side into junction area. So here, because of pumping source, that means for the forward bias, already the influence of forward bias, electric field conduction electrons will be injected from N side into the junction area, while holes will enter the junction from P side. So again, we can obtain the recombination of holes and electrons in the depletion region. Thus, depletion region becomes thinner, very, very thin. We can observe a depletion region here. So optical resonator system. Already the two faces of semiconductors which are perpendicular to the junction plane make a resonant cavity. That means bottom surface of p-type semiconductor, top surface of the n-type semiconductor. In the figure itself we have seen here. See here, and this one act as the here, those two are act as a resonant cavity, and top and bottom surfaces of layer are parallel to the junction plane, are metallized so as to make the external connections, which we are given the connections, battery connections. Those two are metallized, which are parallel to the junction plane. So front and back faces are roughened to suppress the oscillation in the unwanted direction. Front and back roughened surfaces to suppress the oscillation. Here this one back side, front side and back side. So to suppress the oscillation in the unwanted directions. Now what are the examples of semiconductor latches? Gallium arsenide, and which is heavily doped semiconductor, and its N region is formed by heavily doped with tellurium in a concentration of 3 into 10 power 18 to 5 into 10 power 18 atoms per cubic centimeters, while P region is formed by doping with the zinc concentration around 10 power 19 atoms per cubic centimeters. That means here semiconductor latcher which we have chosen the gallium arsenide. Here we are and here N region is formed heavily doped with the tellurium with a concentration of this much, and P region is doped with the zinc concentration around 10 power 19 atoms per cubic centimeters. Let us see the space between the bands in the energy gap or forbidden gap. And this is a conduction band, this is a valence band, and here in between the gap is nothing but band gap, and this in the upper direction we can see the electron energy. And suppose if you see valence band, this is the conduction band. Here in the case of valence band, we can observe the um, what we can see it here. So here this is the valence band which is filled band, and this is the conduction band which is empty band. This is empty, and here the gap here we can say it as Fermi level, or we can say forbidden gap. And here optical pumping from the lower energy level straight to the conduction band higher energy level. As we get as we are giving some pumping, the atoms which are present in the valence band, it goes to the conduction band, and from here to here, while it is transition from higher level to the lower level, we will obtain some photon energy here. This is the space between bands in the energy gap or forbidden gap. And let us see the working of a semiconductor laser. So achievement, how can we achieve a laser? So the electrons recombine with the holes in a junction region. So how can we get the lasing action? Electrons recombine with the holes in a junction region. There will be release of energy in the form of photons. That means when the electrons and holes recombine in the junction region, we will obtain the photon energy. It will release photon energy. So this release of energy in the form of photons happen only in the semiconductors like gallium arsenide. Not for all the materials we won't attain the lasing action. So semiconductors like gallium arsenide will obtain the photon of energy. It will release some laser action. But if we consider the semiconductors like germanium, silicon, so whenever holes and electrons recombine, it will release the energy in the form of heat. That means it is not the laser. So this is not the for the production of laser. So the spontaneously emitted photon during recombination in the junction region of gallium phosphate will trigger laser action near the junction diode. That means only some of the semiconductors only they produce the laser, but not all the semiconductors. That means the germanium, silicon, they produce the heat, but it is not the lasing action. Gallium arsenide, they produces the lasing action. So photons emitted have a wavelength of 80 to 100 angstroms to the 9000 angstroms in the infrared region. So how to make energy levels diagram? Let us see it here. So what is the concept of Fermi level? So Fermi level is nothing but it signifies the probability of occupation of energy levels in the conduction and valence bands. So if we consider the extrinsic semiconductors, number of electrons in the conduction band, which is not equal to the number of holes in the valence band. That means conduction band, electrons are the majority charge carriers. In the case of valence band, holes are the majority charge carriers. So in the case of extrinsic semiconductors, number of electrons will not be equal to the number of holes. That means both are unequal. Therefore, how can the Fermi level for the n-type semiconductor lies close to the conduction band? That means the Fermi level, which is in the case of n-type semiconductors, the Fermi level is close to the conduction band. And for the p-type, holes are majority charge carriers, so Fermi level which is close to the valence band. So what are the advantages of the lasers, semiconductor lasers? It has a high efficiency, wide wavelength range, Bluetooth infrared region, highly compact, low power requirement, easily modulated, power output 1 megawatts to 10 watts, wavelength range is lambda equals to 400 nanometers to 10 to 12 microns. So what are the disadvantages? Lower peak than gas lasers. We will obtain a lower peak when compared with the gas lasers. So problem with variation of temperature, instability, etc. So this is about the lasers, semiconductor lasers. Thank you, children.